Here's the proof for Lem2, and I'm going to walk you through it. It's pretty straightforward. So first of all, since the implications from 3 to 2 and 2 to 1 are clear, okay, it's easy to see that if you can, if you can break up a n summand or a linear combination of n vectors, that means that you could do it for 2 because n would be equal to 2. So that, I mean, that's clear that this implication exists and is valid. And the implication from this to this, because if you could do it for 2, then that means that it implies that the statement 1, which is the two operations that it preserves structure, right, holds. Okay, so what we need to do, we only need to show that 1 implies 3. In other words, if the f preserves structure, then we can use it to break down finite vector linear combinations. Okay, so how do we do that? Well, it's an implication, so we're going to start with the hypothesis. So we're going to assume this. So we assume statement 1, okay, which means that f preserves structure. And so we're going to prove 3 by induction on the number of summands n, right? So it's a linear combination of n vectors. So we're going to start with the 1 summand base case, which is just this, right? Just 1. So, but this is covered in statement 1, right? So under scalar multiplication, right? So that's covered under statement 1. So the base case is already covered. Now for the inductive step, we're going to assume statement 3 holds whenever there are k or fewer summands. So remember, so anything from 1 to k, we're going to assume that it holds, that that 1 holds, statement 1 holds for all of those. Okay. Now what we're going to do is we're going to show that it also holds for k plus 1, the k plus 1 summand case. So now what we're going to do is we're going to use the first half of statement 1. The first half of statement 1 says that you can break up across the plus signs. But in this case, we're going to use statement 1 to just break up this linear combination of then k plus 1 vectors into 2 pieces. We're just going to break it off at the final plus sign so that the k plus 1 term is here and the rest is here. So we're just going to apply statement 1 at this point. So we know that we can break it here using statement 1. Now, but look what happens here. Look what you have. Now you have what? F applied to a linear combination of k summands. So by the inductive hypothesis, we can use statement 1 to break this up. And so we can break this up into a linear combination of functions applied to the vectors. So we could break this up into C1 times f of V1 plus C2 times f of V2 all the way to C times f of V sub k. Okay? And then what do you have? But now if you do that, what do you have? You have a full linear combination of what? Of everything from, you have k plus 1 terms, right? So what you actually end up is, you end up with C1 plus, or excuse me, C1 times f of V1 plus C2 times f of V2 all the way to C sub k times f of V sub k plus C sub k plus 1 times f of v sub k plus 1. Why? Because 1 also applies to only having one summand. Right? Because at this point, once we break it up, the second part of statement 1 gives you the scalar multiplication. And then you're done, because we just showed that it was applied to k plus 1 vectors. And so therefore, statement 3 is proven. And that's it.